All right, so very good. Slides are in place, and I guess if everyone's ready, we can start for today. So it's my pleasure to welcome everyone to VAMOS today. Today will be the last of this season. So stay tuned for the next installment, I suppose, in fall 2023 here. We're really pleased that Dan Stamper-Kurn was able to join us today to give today's VAMOS seminar. As many of you know, Dan did his PhD at MIT and followed that with postdoctoral work at Caltech. He's been at Berkeley ever since, where he's currently at the physics department and also the Challenge Institute for Quantum Computation and the Material Sciences Division at Lawrence Berkeley National Laboratories. Dan will talk to us today about exploring measurement and feedback with ultracold atoms in an optical cavity, and I will let him take it away. Just one reminder maybe before, if you have questions throughout the talk, please use the Q&A tools in Zoom or on YouTube, and we'll collect those questions. And I see Bill Phillips is here, and you can email me questions too, if that's easier for you. So with that, Dan, please take it away, and we'll look forward to your talk today.
All right. Hey, thanks for the invitation. Great to participate in VAMOS. What a great institution. I'm glad to see it's still going strong, and it has it can still pull us together from all of our distant perches. So I'd like to tell you about, let's say, kind of half of what's become my research program at Berkeley, which has been in the area of the interface between ultracold atoms and quantum optics. And by way of a very broad introduction, I'll just point to the following, that many of us are thinking hard about constructing, controlling, and then eventually utilizing many-body quantum systems for all sorts of purposes. And you know, for those of us working in atomic physics, working with trapped atoms or ions, it's pretty natural for us to use light as the medium for orchestrating what goes on in these many-body quantum systems, right? So this is because we have objects that are optically active, and we know enough about atomic physics to know how to orchestrate all sorts of manipulations of these atoms. And this light, in fact, ends up serving a lot of purposes for us if everything is going well. So, you know, so one standard thing we might do is shine light on a system and look at the scattered light and use light then to detect. So then I would regard light as being sort of an information carrier. And there's a channel of information coming off of the atom going off into our detector, and we can determine the state of our many-body system. Sometimes this light is used to cause the system to undergo transitions from one quantum state to another, whether these are, you know, single particle transitions or maybe something fancier in a nonlinear system. And with regard to that, we also use light to induce interactions between atoms. So, you know, famously, let's say these days in the context of Rydberg gates on cold atoms, but also for trapped ions, we end up coupling atoms and using light to orchestrate the process. So light is our friend, but light is also our enemy. So you know, because the interaction between atoms and light is not, you know, completely controlled in a setting like this, a lot of light can just slip out. So we can shine light onto a system that we want to use to create a particular purpose, but other photons may now emerge in various directions that are a little bit out of our control. And all that scattering out into all directions kind of it foils our attempts to make this many-body quantum system do what we do. So in terms of detection, if we scatter light to the heavens, then that's wasted information because we're not gathering it. So that we could have made a more sensitive measurement. And that light that slips out also might reveal something about our quantum system that we otherwise wanted to keep hidden. In terms of the ability of light to drive quantum state transitions, what we might find is that there's maybe Raman scattered light or something which can cause the many-body system to go into states that we didn't intend for it to occupy. Maybe these are also states of motion, and that corrupts our system. And then finally, related to that, if we're using light to orchestrate some kind of interaction between different quantum objects, you know, light that is exchanged between the two objects perhaps is doing exactly what we want it to do, but light that scatters out can end up causing an error in things like our gates. So for this reason, it may be advantageous for us to try to control this light atom interaction, not allow the atom to interact with all sorts of modes of the electromagnetic field that we didn't mean for it to interact with, that are just spoiling our physics, but really constrain these objects to interact just with modes of light with which we're trying to accomplish all these quantum tasks. And that sort of justifies this field of cavity quantum electrodynamics, where by placing atoms or quantum objects inside of a cavity, we can at least accentuate the interaction with a particular mode of light, and potentially in other cases, even suppress the interaction with other unwanted modes of light. And now light atom interaction becomes much more deterministic. And this general scheme of cavity QED, one or more quantum objects interacting with light inside of a cavity, driven by light either coming directly to excite the cavity or to excite the quantum objects, and then leaking light out into, let's say, a detector, can be used for a really wide variety of physical setups. So for example, one way to rig up a cavity QED system is to enhance or to utilize it for detection. So in this case, the idea is that the quantum system will have a strong influence on light inside of the cavity, and light can then emerge from the cavity and very efficiently go into a detector, and we can use that for fast, highly sensitive, maybe quantum limited detection. So one of the topics I'll talk about, actually the second topic I'll talk about, is an application of this idea to perform mid-circuit measurements on atoms inside of an array of optically trapped atoms. Another setup we might consider is to focus on the fact that two atoms inside of a cavity can exchange photons. So we can have a situation where we drive one atom. That atom might scatter, emit a photon, but rather than that photon leaking out and being lost, it might resonate inside of a cavity and reside there long enough for a second atom to pick up that photon. And now real photons have been used to mediate an interaction. And this can be used to create an interacting quantum system, which is linked together by light. And I'll talk about some ideas related to this, where we're now studying how a collection of atoms interacts with light inside of a cavity, and ideas for how that's going to lead us eventually to a kind of quantum gas microscope to study open quantum phase transitions. Another extension of this idea is feedback control. So there's a couple of ways in which you might try to implement feedback on your many-body quantum system using light. One of them would be to simply allow the light to leave the system, to be recorded on some classical measurement device, and then use that information very quickly to modify how the many-body quantum state interacts. And so that would be like a measurement-based quantum feedback protocol. Alternately, there's also autonomous forms of feedback where the dynamics of the system itself acts in some kind of negative feedback form. So we can have the atoms inside of the system evolving in a way that they place light in the cavity, which is then conditioned and acts back on the atoms, and that can give us a form of feedback stabilization. And that'll be actually the first topic that I speak of. And then there's a lot more in the world of cavity quantum electrodynamics, also waveguide quantum electrodynamics, some of which is happening in my lab and very much of which is happening in a lot of other research groups. So this remains this union of ultracold atom, or maybe also molecule physics, with quantum electrodynamics is a pretty rich field altogether. But as I said, this is the sequence of topics I'd like to talk about. Let me first talk about autonomous stabilization of a spin ensemble. Okay, so here's actually a picture of the experiment where this takes place. And inside of this experiment, maybe you can see in this photo, there's, okay, you can't actually see. There's a little silicon atom chip right here. There's one piece of a cavity. Here's one mirror. The other one is hidden behind this piece of copper. So if I drop this piece of equipment and it cracks in half, then I can take a nice picture of it. So here's the setup we use. This is an experiment we've been using for a long time. You see the first paper comes out in 2010. We use an atom chip. So you remember atom chips where we place electromagnets inside of a wafer to move around atoms that are above the surface of the chip. We use an atom chip to bring an ensemble of atoms, turns out to be rubidium-87 atoms, and place them between two mirrors, and the light bounces back and forth between these two mirrors, forming a high-finesse cavity. This high-finesse cavity achieves the strong coupling regime of cavity QED. So single atoms and single photons are strongly coupled. And the atoms inside of this cavity experience two light fields. One of them is this trapping light. So we use light that's very far detuned from the rubidium atomic resonance. And this forms a standing wave of light inside of the cavity. And with our atom chip, we can place a few thousand atoms in one well of that standing wave. So we place them in a pretty well-defined location, at least along the cavity axis, and we have a few thousand atoms residing within that one well. Now we come along with probe light, or maybe we'll call it pump light or whatever, but light that is also near resonant with one of the cavity modes. And this light is fairly close, I mean, still 30 gigahertz detuned, but fairly close to one of the atomic transitions in rubidium at, excuse me, at 780 nanometers. And this light, okay, does some interesting physics with the atoms, and a lot of our information is obtained by taking the light that comes out of the cavity and sending it to a heterodyne receiver. So that's going to be the setting for this work. Okay, so inside of this cavity, now I've turned it sideways, we have atoms that are in a tight trap. This is a trap that's produced optically. And they're placed at a particular location within the mode structure of the pump field. So this blue line is supposed to represent light at 780 nanometers. And for these experiments, we place all the atoms at locations where they're at an antinode of that field. So the intensity of that mode, which is given by this quantity here, is maximum at the location of these atoms. These atoms are all driven or interact with a cavity mode that is fairly off resonance. I mean, it's 30 gigahertz off resonance, and that qualifies the interactions as being largely dispersive. The effect of that is that each one of these atoms acts like a little bead of glass and puts an extra phase on the probe light. And the effect of that is that it shifts the resonance frequency of the cavity by a fixed amount. We have many atoms inside of this ensemble, maybe a few thousand. And so the overall frequency shift is this quantity. So it's n times the frequency shift by a single atom. And the fact that the frequency of the cavity is shifted by an amount proportional to the number of atoms is something that we've been using for scientific purposes. So here's a paper that I think is pretty cool, but I won't have time to talk about, where we make real-time measurements of an atom that undergoes evaporative cooling, so a non-equilibrium thermodynamic process. And we try to track not just the average dynamics of evaporative cooling, but also fluctuations that occur in the mesoscopic regime. Okay, so that's something that we can monitor in real time and monitor quite sensitively. Okay, now let's add some complication. So it turns out that our cavity actually supports two near resonant modes. It's just about the same frequency. These are the two, let's say, circular polarized modes of light. And in addition, the atoms that we have, these rubidium atoms, are not just two-level atoms, but they're atoms that have an internal degree of freedom, the spin degree of freedom. We trap these atoms in the F=2 ground state, so each one is a spin 2 object. And it turns out that the interaction between the atom and the light field depends mutually on the spin of the atom and the helicity of the light field. There's a vector term to the atom-light interactions. So now the frequency shift by a single atom is not just proportional to the number of atoms, but also to the spin of the atoms, and in particular, the projection of the spin of the atoms along the cavity axis. So here, if I look in the many atom situation, the cavity is shifted by one quantity, which is just proportional to the number of atoms, but another quantity that is proportional to the total collective spin along the cavity direction. And it's with this spin sensitivity that we can now have our cavity do some interesting stuff interacting with the quantum collective spin of the gas of atoms that's trapped inside of the cavity. Okay, so this idea of looking at dynamics of spins inside of a cavity sometimes goes by this Frankenstein name of cavity optomagnonics, I guess kind of related to cavity optomechanics, but really just supposed to summarize this cavity QED setting of like a mutual interaction between light and spins. When we first thought about this idea, we thought about it very much in analogy with cavity optomechanics, which is an area where my group has done research for a while. So this is now a little bit historical. We noticed that just as in an optomechanical system, the state of a particle undergoes precession in its phase space, and a cavity can be sensitive to, let's say, one quadrature of that motion, like the position of a mirror or of an atom rather than its momentum, leading to cavity optomechanics. Similarly, we now have a system where, let's say, if we apply a transverse magnetic field to our atomic ensemble, the atomic spin will undergo precession in its own phase, in its own space. It undergoes precession within the transverse spin degrees of freedom. And in this configuration, we have a cavity that senses one quadrature of the precessing transverse spin. So from that, we started developing the ideas that all of the physics that we had become familiar with from the study of cavity optomechanics, including cavity cooling or laser cooling of mechanical motion, should also apply to the physics of a spin that precesses inside of a cavity. So here's an example of what can happen. So let's say we have a spin in this configuration, or this is our collective spin, and it's prepared somewhere on the in a particular state. Okay, I don't know if I should call this a Bloch sphere, but it's prepared at a particular state. And now we send light into the cavity, and let's say that light happens to be blue detuned from the cavity resonance. Okay, great. So now we have this precessing object. It's undergoing a lot more precession, which means that the frequency of the cavity is being modulated, right? Because the resonance frequency of the cavity is proportional to the spin along this cavity axis. All right, so that means that this light that we sent in, now running into a frequency modulated cavity, acquires sidebands at the Larmor frequency. Now, a frequency modulator in free space produces sidebands with equal power. The red and blue sidebands have the same power. But this modulator is inside of a cavity, and so you might imagine that this modulator produces more light on the sideband that's closer to the cavity resonance. So there's a sideband asymmetry now in the light that emerges, and that means that there's also a change in the energy balance of the system. So if I look at the light, in this case, it looks like more light has been shifted to the red. So the light comes out with less energy. That means the spin must have been left behind with more energy. And in fact, the physics that ensues is that the atom is deterministically driven from whatever its initial state is. It ends up deterministically being driven so that it comes to a steady state, balanced somewhere, in this case, near the high energy pole. The high energy pole was selected because we blue detuned this probe light from the cavity. If instead we had driven the cavity on the red of its resonance, we would have driven the atoms down to the low energy pole. Okay, so this is something that we observed back in 2017. We can look at the light coming out of the cavity. That is, we can look at this modulated light coming out, and from it, make instantaneous measurements of the atomic spin. So we see the atomic spin undergoing its precession, but you see that its magnitude diminishes, and that's because in this case, we are cooling our atoms toward the high energy pole where they become stabilized. And we thought about this and realized there's some physics here which looks a lot like a feedback system, but let me go a few slides forward before I really characterize this dynamics in the form of feedback. But anyhow, knowing that there's something like feedback, we wondered, can I use this feedback to stabilize my atoms at a wider variety of states than I have in the picture that I've shown you so far? So as I showed you in this graph, if I blue detune my probe light, I'm going to stabilize, I'm going to, by feedback or whatever, however I'm describing it, I'm going to send my atoms to the highest energy state or something near the highest energy state. And if I drive the cavity to the red, I'll drive my atoms and stabilize them near the lowest energy state. But how can I stabilize them in maybe some arbitrary spin state? This is an appealing thing to do. So generally, there's a field emerging which studies how to control quantum systems by means of feedback. And the motivation for wanting to think about this is pretty compelling. For one, if you look at just about any classical technology around you, it operates as well as it does because feedback is built in. I mean, my iPhone is working really well right now, and that's because all of its electronic components are internally stabilized by feedback. Feedback also has application. So if we think about any quantum technology that we might want to develop, the quantum computer or whatever it is, chances are it's going to operate robustly because feedback is employed. So we should learn how to do that. Feedback is also useful in the context of sensing. So there's applications in classical sensing where we use feedback in order to extend, for example, the dynamic range of a sensor. And a fine example of that is this bubble level inclinometer. So a bubble level, right? You remember there's a bubble and it can tell whether or not your surface is tilted with respect to the horizontal. But what if you wanted to know whether your surface is exactly at 43 degrees? How do you use a bubble level for that? Okay, so you mount something on the surface, and here you just turn a protractor by feedback until it's sitting at 43 degrees. And now your bubble can be used to sense the deviation of your surface away from 43 degrees. So that extends the dynamic range of a bubble level sensor. And this applies in other measurements as well. So we can imagine that quantum sensors employing feedback will be more powerful. And then finally, just the question of how does in particular, many-body quantum system evolve in the presence of feedback control is just a dandy of a physics problem, and something that I think will lead to a lot of fundamental insights about non-equilibrium quantum science. So anyhow, that motivates us to think about feedback. All right, so here I am, I'm an experimentalist, and I've learned all about feedback systems. And this is what I see in a textbook. So feedback operates typically as follows. There's a system you want to stabilize. It's called a plant, I guess, because you're stabilizing some, I don't know, chemical industry plant or something. Anyhow, this is the system you want to stabilize. And the way you stabilize it is there's a particular property of it you want to stabilize. So you sense it, you make a measurement of it. You take the output of that sensor and you put it into a comparator that compares what you've sensed about your system to a set point that you've established from the outside, some voltage or some knob setting or something. The difference is the error signal. That error signal is sent into a device called a controller, which you build, and you design it so that when this controller now acts on the system, it applies negative feedback and it stabilizes the system unconditionally. So whatever is the initial state of the system, it'll be brought to the right level. And also, if this system is subject to additional disturbances, then the effect of those disturbances might be ironed out. Now the question arises, how is this different if the plant I'm trying to control is a quantum system? That would be like quantum control theory. So there's a couple of kind of standard approaches that people have thought of. One of them is measurement-based feedback. Okay, so we take a quantum system, and then let's measure something about it. Now, we don't want to measure everything about it because now it's just a classical system. So we measure some property of it with a particular sensor that now brings the information into the classical world. In the classical world, we do our electronics, we take a difference, we run a controller, and then this acts back on the quantum system by whatever transducers we have. How is this anything distinctly quantum mechanical? So it looks like pretty similar to classical control theory. The quantum mechanics comes about in the fact that you have to recognize that when you sense a quantum system, you disturb the quantum system, and also your measurement is necessarily not very precise. So that's the sort of the dual sides of quantum measurement noise. And also based on the imprecision of your sensor output, because you're making an imprecise measurement on this quantum system, you have to think hard about what is your estimate of the system, not just what you predict its state to be, but also account for how much uncertainty you think you have remaining. And you have to design your feedback protocol appropriately. Okay. Another approach to feedback is actually to keep this entire diagram quantum mechanical. So that's goes by the name of autonomous or coherent feedback control. And it would be realized in a system where somehow effectively in your quantum system, still in the quantum space, there's something that acts like a sensor, a comparator, and a controller. All right. So here is our idea for autonomous feedback stabilization in the context that I just spoke of light interacting with a collective spin. And it's very simple. All we do is we have exactly the same physical setup as before, but we take the magnetic field and we tilt it at an angle. So that now the projection of the spin that is measured by the cavity is neither purely the longitudinal spin along the cavity of the magnetic field axis, nor purely the transverse spin, the one that's undergoing Larmor precession, but rather a combination of both. All right. Now, let me tell you how the different pieces of this Hamiltonian represent the pieces of the feedback circuit I just showed you. So first is this term, which is the sensor. So the control variable in this particular feedback circuit is the longitudinal spin, or the energy of the quantum system. And it is sensed, so to speak, because the cavity resonance frequency is shifted by an amount proportional to that longitudinal spin. Now, at this input to the cavity is driven, and it's now important, if we want to think about the response of the cavity, what counts is the net frequency difference between the frequency with which I drive my system and the spin shifted cavity resonance. Okay, so the effective detuning of the probe light or the pump light from cavity resonance is given by this expression. You see a minus sign here, and that qualifies this as a comparator. With this quantity, this difference, this detuning here being the error signal for our feedback system. Okay, so for example, this sketch over here might pertain. So let's say we drive our system at a particular frequency. If we start with an initial state where all the atoms are maybe in their maximum energy state, so at the high energy pole in spin space, maybe the cavity resonance is shifted over here. And in this point, the effective detuning of the probe from the cavity resonance is negative. Or if all the atoms are sitting in their minimum energy state, then this set point equation, or this equation for the error signal, would show me that the net detuning of the light would be positive. Now, how does this feed into a controller? The controller is represented by this last term, which is the sensitivity of our cavity to the transverse spin of the atoms. And so by the explanation I just gave you, this sensitivity to transverse spin leads to this cavity cooling effect. All right, so for example, in this diagram, let's say we drove our system with this green light, and the atoms were initially in this maximum energy state. In this case, the green light is red detuned from the cavity resonance, and that leads to cooling. So it would reduce the energy of the spin system. In fact, until the spins brought the cavity right into resonance with this green light, we would now have equal power in the two sidebands and the feedback would have been completed. Conversely, if I had my atoms start off in the minimum energy state, then now the cavity is red detuned from the probe. That's a condition for amplification or for cavity heating of the spins, and the spin energy will now rise. So that's the feedback mechanism. All right. So here's some experimental data that shows that this feedback idea works. So I'll show two types of measurements. In the first, we take our spins in the cavity, like I've shown you. We tip them to 90 degrees, so we put on a pi/2 pulse, and we apply stabilization with probe light at different frequencies. And we characterize the system by two different means. One is we can take the light that comes out of the cavity onto a heterodyne receiver and measure separately how much power is on either the red or the blue sideband. So let's look at this example. In this example, where we set our cavity pump light or cavity probe light is trying to stabilize the spins to a low energy state, lower than where they are at the equator. And you see that indeed at early times, there's more power in the red sideband than the blue sideband. Oh, sorry, is that the opposite? Okay, maybe I have things a little bit reversed. Anyhow, so this, you're right, sorry, this is wrong. This is actually trying to stabilize atoms in the high energy state. And you can see that there's more power in the red sideband than the blue sideband. The power difference we can keep track of as a function of time. So here you really see as a function of time, the energy that's being transferred to the atomic spin. And it takes the atoms from the equator and pushes them somewhere else to some different steady state. Likewise, if we pump the cavity on the other side of resonance, then there's more power in the blue sideband, which means that we're taking energy out of the spins, and you can track the evolution of that in real time also. Alternately, we can just measure the atomic spin after we've applied feedback for a while. And here you see, let me focus, for example, on these data at 75 degrees. That's the angle of this magnetic field. We see that depending on where we place the pump detuning, we can drive the atoms either to the F equals 2 state, the M equals 2 state, the M equals minus 2 state, or really anywhere between smoothly. And by examining the slope of this curve near zero, we're able to basically confirm this set point equation quantitatively. All right, another thing you do when you have a feedback system is you characterize its spectrum. So if I'm in the lab, I would put a spectrum analyzer, or maybe I would look at the impulse response function of my feedback system. So the way we do this is we start with the atoms so that the average spin is, let's say, -1 per atom. And we turn on feedback, which is attempting to stabilize them just above the equator, where the average is +1 per atoms. And we measure the spin as a function of time. We watch this evolution. And just approximating the evolution, I mean, there's some complications here, but approximating the evolution as exponential, we obtain a time constant, which is related. It's basically, it quantifies, if you will, the closed loop gain of the system. I won't go through details. We have a functional understanding of what this time constant should be. And what we find from our theoretical treatment is something fairly close to what we expect. So we've realized and characterized this autonomous feedback system. Now, you should be critical, and you should ask what part of these experiments that I just spoke to you about is actually very quantum, and to what extent would a classical treatment of a classical gyromagnet essentially get all of the same physics? Well, now let's ask some more detailed questions. So one of them is, what is the steady state that's achieved by this feedback? Is it possible that by feeding back to the energy of the spin system, we can reduce, or we can actually project the system all the way to an eigenstate of energy, a Dicke state? I don't think that that's the answer, because we're also continuously measuring our quantum system. And in fact, energy is not a QND variable when you also have optical effects that look like a torque in a direction not along the magnetic field. Okay, so we have to think about what the steady state is. I'm not really sure what it is. Another one is, what about fluctuations? So this system works and autonomous stabilization works, but it's also the case that the light inside of the cavity also has fluctuations. It has a spectrum of fluctuations given by quantum optics. And that produces a fluctuating torque on the atoms. And that would disturb the steady state of the system, would lead both to noise in the phase direction. So the Laumer phase should sort of diffuse around, and also would put noise onto the longitudinal energy, because there's also a torque that pushes in the longitudinal direction. Characterizing this energy noise, I would expect that quantum optics feeds noise into a system, and feedback suppresses that noise according to the closed loop gain. So if we can characterize these fluctuations and knowing about the dissipation, we should be able to clarify the relation between them. That would be definitely a very quantum mechanical signature. At this point, our system is just too noisy to make that measurement. We've also been asking ourselves, can we also stabilize not just the energy, but also the phase of the precessing collective spin? And I think there's a way to do that. We have to break time translation invariance of our feedback system. So I believe that if we just modulate the control variable, or sorry, the set point, or we even modulate the magnetic field acting on the atoms, we should be able to stabilize in the phase quadrature as well. Another open question we've been considering is, can we append measurement-based feedback on top of this autonomous feedback? So as you've seen, there's information coming out of my cavity. I can actually measure the Langmuir precession in real time, and I should be able to use that now to feed back onto the quantum system also. That would be interesting to do. And then last, we wonder whether we can get out of the regime of just looking at the stabilization of the spin of an ensemble of atoms and apply things like feedback stabilization in more of a many-body context. And for that, I guess it would behoove us to go away from doing cavity QED with ensembles of atoms down to cavity QED with really something more like a controlled array of atoms. And that then leads me into the second half of my talk. But maybe at this point, I can take questions.
Yes, great. Thanks. Very interesting. So there are some questions here. Maybe I'll start with one from Bill Phillips. The description of active stabilization looks like a proportional controller. Can you do a quantum version of PID?
So thanks, Bill. This is actually an integrator. So you see that it damps it damps any deviation of the spin at an exponential rate. So it's really so anyhow, it's equivalent to an integrator, right? Where if the modulation is where there's a 1 over frequency, or I guess there would be a 1 over frequency in the closed loop gain. Now, so this is an integrator. It stabilizes it stabilizes with no offset, I guess, from which proportional gain would have done. Can I add other features like other frequency features now add proportional or differential gain? I would have to think about that. That's a great question.
One other question from Bill. What if you had tensor light shifts, ignoring the problems of being close to resonance? I now have something besides spin. How should I think about that?
Yes, good question, Bill. I don't know. We actually purposely do the experiments away from. Okay, there's the tensor light shift. There's also the quadratic Zeeman shift. We do the experiments in a regime where we don't have, within the time of the experiment, we don't have to think about the quadratic Zeeman shifts. In terms of the tensor light shifts, I would. It's a great question. Even in control theory, in classical control theory, the books I have here on my shelves, they talk about like the group of all the control operators that you have on a classical system, and you try to make that group rich enough so that you can control all aspects of your classical system. Maybe there's several aspects of it that you want to control simultaneously. So similarly here, you're suggesting we add another set of operators, and then in time dynamics, we end up with a group that spans a lot of properties of the collective spin system. Great question as to where that leads. Somewhere interesting. I don't know.
Great. There's one more question from the Zoom Q&A. Again, sort of along the lines of feedback systems. It says to test the feedback control, one can apply a step function to kick it out of equilibrium and then see it come back. Has this kind of test been observed in the system? Yeah,
so that's exactly what's done here. That's the impulse response function. We actually started it with a fixed distance away from equilibrium and watch it relax. Another way to characterize a feedback system is also to stick it into a network analyzer. And we've done that as well. So under feedback, we've done things like modulate the input pump frequency, and then look at the modulation of the spin in response. And I don't show the data here, but we have like a curve of what should be the closed loop gain of an integrator circuit. And that works moderately well. The signal to noise for that particular measurement wasn't wonderful. So I decided to show this part rather than the other, but we've done both.
Okay, I think let's go on to the second half of the talk, and we can ask some more questions later.
All right, great. Thanks, everybody. Love the questions. Next is okay, so I guess I set the stage. Let's try to put something more interesting inside of a cavity. And so now I want to talk about a somewhat newer experiment in my lab, which is, let's see what happened here, which is placing, in fact, a tweezer array inside of a cavity. So I think if you've been attending the VALMOS seminars or if you're still an atomic physicist who hasn't been under a rock, you've heard about tweezer arrays as really being the next revolution in ultracold AMO physics. And I don't need to describe in detail how these work. Well, I guess I'm going to go ahead and do so anyhow. So you create, let's say, a lattice or whatever of optical traps. Each trap ends up holding either one or no atoms inside of it after you've applied laser cooling to these atoms. On a camera, you find out which of the many traps that you've laid out has caught a single atom. And then based on that information, you resort the tweezers so that you end up with exactly the number of atoms in a set of tweezers that you want. So this is a movie taken roughly real time in my lab downstairs, where we've now learned how, in this video at least, to load 16 tweezers initially with atoms, and then using a camera and some processing to quickly shift the trap so that there'll be 6 atoms in a row. And now that's in our lab, it's up to maybe 25 atoms altogether. But we're really novices in this. There's people that make very fancy large atom arrays and use Rydberg interactions to create interactions between atoms in these Rydberg arrays. And in very short order, all of these just amazing results have come out. And even you can, I suppose, if you're bored of listening to me, you can go online and program a quantum simulator in real time and answer cool physics questions. Okay, so this is a great technology, and we would like to, or a great new technique, and we would like to integrate it with cavity QED for a couple of reasons. One is maybe there's some benefits that cavity QED can provide to the physics of atom tweezer arrays. Like, for example, the effort to make a quantum computer using tweezed atoms. So there's some novelties that the cavity gives you. So for example, atoms inside of tweezed atoms inside of a cavity can interact not just through the Rydberg interaction, but maybe also by swapping real photons. Maybe we can get interactions at long distance or different collective types of interactions. Secondly, a cavity is really good at collecting light from the atoms that are fluorescing, or just at amplifying the interactions between an atom and light, and that can lead to fast measurement. And that's an application that I'll tell you about. And then you can also imagine that surrounding a Rydberg quantum computer module with a cavity would allow you to transduce quantum information into light and maybe have it go into another computing module downstream. So there's reasons to move in this direction. But also for the physics of cavity QED, tweezers are like a really cool new approach to making interesting physics, because now we can, load really rather deterministically a fixed number of atoms inside of a cavity. We can position them in the cavity with essentially nanometer level positioning. So put them at specific locations inside of a light field, and thereby really make something like a metamaterial, a collective of atoms that interacts with a cavity different than a single atom would. So that's inspiration enough. So we built ourselves a machine that does this. And this is like showing you none of the details at all, but we do experiments with rubidium-87 atoms. We built an experiment which in hindsight is way more complicated than it needs to be. In this experiment, we can produce gases of millions of atoms, put them in an optical trap, translate them inside of a cavity. And then from these millions of atoms, we fish out just like 10 atoms using something like 10 tweezers, using a light projection system that is transverse to the cavity. And that's how we start our experiments. The cavity is near concentric. The advantage of that is that the cavity mirrors are far distant, so that gives us a lot of transverse access to the atoms. And this cavity system is sort of on the verge of strong coupling. So it's not a wonderful cavity. The cooperativity is like 4 or something. But anyhow, that's what we're working with at present. The very first thing we did when we built the system was worry. And what we worried about was that we know how to trap an atom somewhere in the cavity, but how are we going to know whether this atom is in, let's say, a node or an antinode or something of the field with which we want it to interact? The answer came to us pretty quickly. So we were taking these images. These are images of atoms inside of our cavity. Now they just look vertical. Each of these dots is a single atom. So I can tell that this tweezer holds an atom and this one doesn't. But it also turns out that if I count the number of photons in this image, I have another bit of information, because now I'm roughly measuring the fluorescence rate of this atom in the tweezer. And the fluorescence rate turns out to be proportional or inversely proportional to the detuning of the, I guess it should be this should have been squared, is related to the detuning of this probe light from the atomic resonance. Now, if there's some local condition, for example, an AC Stark shift, again, this should be a 2, I believe. If there's some local AC Stark shift that shifts the energy, the resonance frequency for the atom, this should end up changing the amount of fluorescent light that arrives at our detector. And in fact, that's something that we see. So now we can think about using single atoms and tweezers and a camera that measures their fluorescence all together as like a scanning probe microscope. And this atom senses the intensity of light locally. So in this case, the light that it senses is a standing wave of light inside of the cavity. This standing wave happens to be at a wavelength of 1560 nanometers. So the length scale here is 780 nanometers. And as we drag this single atom stylus through this light pattern, we can see the light intensity and thereby measure the Stark shift of the atom to vary sinusoidally, and that maps out the local intensity of the light field. So this was kind of a nice side project, something about quantum sensing with single atoms and tweezers. But here, the main message I want to give is that we know where the atom is inside of the cavity. And knowing where the atom is inside of the cavity, we can now start doing interesting physics related to cavity QED itself. So first I'll tell you an example of like how we're using cavity QED to improve the physics of tweezer arrays, and in particular, how we realize something called a mid-circuit measurement. And the idea is this. So in a Rydberg tweezer experiment, fabulous experiments, there's nevertheless a couple of limitations. One is that when you measure the atoms in this tweezer array, it takes a long time. You send light in, the atoms fluoresce, but you collect only a very small numerical aperture of the light coming out. So you have to wait a long time for enough light to show up on your detector to see whether there's an atom there and what state it's in. It would be nice to speed that up. Secondly, the measurement is typically done globally. You send light, all these atoms are very close to one another. You send light on the whole system fluoresces. The entire quantum system is measured at once. But that means that there's certain applications that you had for your quantum computer that are going to be hard to realize, where what you actually want to do is perform what's called a mid-circuit measurement. So in the middle of a quantum algorithm that's running on your array of atoms, there's situations where you'd want to measure just a small part of your quantum system and extract its information and use that information to feed back on the rest of the quantum system that remains quantum coherent. So for example, that's the basis of measurement-based error correction. So we were inspired then to try to make a headway toward mid-circuit measurements that would be both fast and also localized to just one atom within an array. And the way we thought about doing this was to have an atom array. In our case, it's only 2 atoms, but to have an atom array. And when we want to measure a part of the array, we would basically just translate that atom into the cavity and use the cavity to make fast local measurements on the atom. So here's the kind of measurement we want to make. I have an atom in a tweezer, or maybe I should say I have a tweezer, and it might contain an atom. That atom might be in, let's say, one level or the other level of my logical subspace. In our case, we consider the f equals 2 and f equals 1 hyperfine levels as like the 0 and 1 states of a qubit. And I want to know which state the atom is in. And maybe I also want to know, incidentally, whether there's even an atom in the tweezer at all, or perhaps whether the atom happens to have been sent to another state that I don't sense. So we try to build a sensor which could make a 3-state measurement. It can tell us whether we're in the up, down, or missing state inside of a tweezer. And the way we decided to do this was to measure fluorescence. So we place the atom in the cavity. We shine light on the atom, which drives fluorescence if the atom is in the f equals 2 state. And the fluoresced light is efficiently sent to a photodetector. Now that tells us whether or not the atom is in the f equals 2 state, but it doesn't give us all of the information. So that, because of that, after a certain amount of probe time, we probe again. And the second time we probe, we add some repump light. The repump light would also tell us whether there's an atom there at all. So preparing the atom in either of the 3 initial states, or preparing the tweezer in either of its 3 initial states, either f equals 2, f equals 1, or empty, we can look at a histogram that counts up how many photons we see in the first period and how many photons we see in the second period. So if the atom was prepared in the F=2 state, we get a bright signal in both measurement periods. So we know that that state was there. If we prepared an atom in the F=1 level, it's dark during the first probe because we haven't repumped the atom, but it's bright during the second. And then finally, if the tweezer is empty, then we get very few photons in either case. And altogether, with this fluorescence measurement, which takes at present about 50 microseconds, we can measure the state of the atom of the tweezer with infidelities that are in the sub% range, which is kind of at the level that you want for certain quantum error correction applications. In terms of mid-circuit measurement, now here's the embarrassing circuit that we implemented. We have an array that's just 2 atoms. The atoms undergo a sequence of single qubit gates, which is to say we drive a Ramsey experiment. But the mid-circuit measurement is done by measuring the state of atom A before the circuit is completed for atom B. And we want to know whether atom B has been disturbed by the intermediate measurement that we made on atom A. And we can do that by moving atom B into the tweezer at the end of the day, into the cavity, and then measuring its state. So here's Ramsey fringes that we obtain for measuring atom B, both with and without the mid-circuit measurement. And I honestly can't tell you which curve is which means that there was indeed very little disturbance from the mid-circuit measurement. And so we find that this mid-circuit measurement has an error of a disturbance less than 3% quantified in certain ways, so long as atom B is sufficiently far away from atom A when it's measured. So this constitutes, I guess, one of the first mid-circuit measurements in neutral atom arrays, and hopefully it'll push the science of that field forward. We intend to add Rydberg state capability to this experiment we're working on at present. I would have gone through this slide about next steps, but I want to allow for a couple of questions and then maybe get to the last topic I wanted to cover.
Great. There's a question from Christian. Depending on the magnitude of the induced light shift in the super resolution localization scheme, it seems one should be able to push the resolution significantly below the diffraction limit. What limits the resolution that's achieved in this experiment?
The resolution is well below the diffraction limit because this has to do with how well you can position the atom. So in this particular case, the atom position uncertainty was probably about 150 nanometers. So we were resolving features with 150 nanometer resolution. I guess you have to think about what is meant by resolution, the Rayleigh criterion, the whatever criterion. But whatever criterion we came up with, it was always smaller than the wavelength of light that we use to measure the atom itself. So indeed, it's a super resolution instrument. Next is about the sensitivity of the sensor. The way we operated the sensor is lazy and dumb. All we're doing is trying to measure the Stark shift on the optical transition. And so, that can only measure shifts on the order of the wavelength or something. Of the line width. Maybe that's what you meant by super resolution. But you could think about other things as well. Maybe we could do some kind of Zeeman energy shift measurement using a Ramsey scheme or something. And then you should be able to measure, local magnetic fields very precisely, also with super resolution in terms of length scale.
Great. Maybe one more quick question, just on the last slide you were talking about. You have this, distance of atom A affecting atom B during the mid-circuit measurement, which seemed like tens of microns, which is probably quite a bit bigger than the tweezer itself. What sort of sets this size?
Yeah, thanks. What sets that is the size of the beams that excite the atom.
I see.
So we're sending in fluorescence light with weakly focused beams, and a little tail of that can affect another atom maybe 20 microns away.
I see. Okay.
So
very good. Okay. Yeah, let's move on to the last part of the talk, and then we'll stop for some questions again at the end.
All right. So next is more recent work. It's in preparation about new stuff in cavity QED that is given to us because we can put atoms in with optical tweezers. And this is the rig that we're thinking about at present. So we take a bunch of atoms, tweezed atoms. They're well positioned inside of the cavity. And we, in particular, pump them from the side. This can be a running wave that comes in from the transverse directions, or actually in the experiments I'll show you, it's a standing wave of light that drives these atoms. Doesn't really matter. Okay, these atoms can scatter light from this pump into the cavity field. And then again, here is the electric field inside of the cavity proportional to this quantity G of Z. It's a sine wave, okay? So I'll just point out that there's places on this sine wave where G of Z is negative, that's labeled in red, and other places where it's positive, where it's labeled in blue, and in between G of Z is 0. All right, so if I just think about the motion of the atoms in this cavity direction, the Z direction as I've shown it, this would be, let's say, the Hamiltonian. We can put photons in the cavity. We can excite motion in the tweezers. Here's the harmonic frequency of the tweezer. And then we have this term, which is the coupling. It's a two-photon process where an atom interacts with a pump field, let's say. This is the Rabi frequency of the pump field at the location of atom I. It produces a photon in the field, and the coupling to the field is given by this real quantity G. All right. Now, each atom couples to the same cavity field, which means, of course, that the light produced in the field is somehow collectively generated by this entire collection of atoms. So, for example, if I took all my atoms and I position them not at these nodes, but at these antinodes, well, then each atom produces a given electric field inside of the cavity, and all those fields add up coherently because they all have the same sign. And now the intensity of light inside of the cavity and the intensity of light coming out of the cavity ought to scale as n squared. This is the famous collective emission, superradiant collective emission from a set of atoms that are emitting coherently. So we set out to just measure this simple effect. And so here's part of how we do so. So in this particular experiment, again, we're pumping with a standing wave, but we're going to put the atoms at a place where that standing wave is maximum. And now just consider two atoms. I trap one atom at the antinode of the cavity field, and the other atom, we will go ahead and translate through some place in the cavity. And then in all these instances, we'll measure how much of the pump light comes out of the cavity. And so here's the signal. And I'm showing here a ratio of how much two atoms scatter to how much one atom scatters into the cavity. So if we place, look at these locations. If I place a second atom, an integer number of wavelengths away from the first atom, then the two atoms collectively, constructively scatter into the cavity. Ideally, I should see 4 times as much light, n squared equals 4. I should see 4 times as much light as I do for a single atom. Or if I place the second atom at a half integer wavelength, so with one atom, let's say in the positive electric field region, the other one's in a negative electric field region, then ideally there should be no emission altogether. The emission of the second atom should coherently cancel out the first atom completely. So ideally we would be here at 0. Okay, so the curves kind of show this super and subradiant response. Not ideally, so we don't go all the way with a contrast from 4 to 0. This has to do with the fact that the atoms are wriggling around inside of their traps, so there's a little bit of a Debye-Waller factor that suppresses the collective response. But nevertheless, you see that this relation holds even when the atoms are spaced super far from one another, because they're all interacting with the same cavity mode. I really love these data. All right, well, let's put more and more atoms into the cavity. So here's, I guess we've recently worked all the way up to n equals 8. And we consider the light coming out of the cavity under 2 circumstances. One is where the atoms are spaced by integer wavelengths. And the other is where the atoms are spaced by half integer wavelengths. These 2 curves here are either an intensity that grows linearly with the atom number or quadratically with the atom number. So first, thinking about the constructive interference situation, we see, in fact, the intensity rises for sure faster than linear. It doesn't go exactly as n squared, and that's because of this Debye-Waller factor. But knowing how much the Debye-Waller factor, or how much the collective scattering is corrupted by uncertainty in the atomic position, we can predict this behavior really quite well. So in that sense, we're seeing the n squared scaling very clearly. We're not the first to be using atom tweezers to look at collective scaling of collective light scattering. There's really nice work that was done by Kuzmich's group in Michigan. But let me also look at these data right here. So here's where we place the atoms by half integer wavelengths. So ideally, what would happen if we had one atom in the cavity, we'd get light. If we have two atoms in the cavity, we should get no light because the second atom scatters the electric field completely. With three atoms in the cavity, I should be back up to here. With four atoms in the cavity, I should have zero light again. We don't have perfectly fixed atoms position-wise, but nevertheless, we can still see this nice even-odd alternation of light intensity, which shows us this sub-radiant response. Certainly, the intensity is growing slower than n times the intensity from a single atom. Okay, so that shows us that these atoms are interacting collectively with the cavity. Now, what's next for us? What's next is to realize that the atoms also, when they put light into the cavity, they respond to the light inside of the cavity. And that can induce all sorts of things, including physical motion. And in fact, in this particular configuration, where I place all the atoms, let's say at nodes of the optical field, in this configuration, they should not put any light into the cavity. But if there happens to be a fluctuation that does put light into the cavity, now the atoms will see an optical standing wave, which might pull all the atoms collectively away from this location. For example, they might all spontaneously produce light that pulls them all to the right. And the atoms would then sort of collectively break symmetry. Depending on how they seeded the cavity field, they would either all spontaneously move to the right or move to the left. This is a tweezer version of what people have otherwise seen in bulk atomic gases, which is the Dickey phase transition in a side-pumped optical cavity. And what I guess I'm proposing to do here is to go from these wonderful experiments, which probe the Dickey phase transition in a bulk gas in a many atom regime, and instead look at it in a mesoscopic regime. And my vision altogether here is to introduce something like a quantum gas microscope approach to studying the Dickey phase transition. As an example, a prototype example of open quantum systems undergoing phase transitions. Okay. I had a slide here where I was going to sort of justify this connection to the Dickey phase transition. I can come back to this with questions, but I don't want to abuse the time. So let me run already to the conclusion slide. Let me thank the folks in my team that have worked on these two cavity experiments that I spoke of. The E3 experiment, which works with like an ensemble of atoms delivered using an atom chip into the optical cavity, and the more recent, the newer generation cavity experiment, where we have optical tweezers inside of a cavity. I want to cite wonderful theory collaboration we've been establishing with a group out at Columbia. And then I did not have time to tell you about work in my group on atoms and optical lattices, or on our efforts to laser cool titanium as one of several transition metals that we want to make ultra cold. But I've already used an hour, so I should probably just stop here.
Well, thank you very much for a really lovely talk. Very interesting stuff, and I'd be happy to listen for a long time. But yes, we'll give everyone some time for the rest of their day. We do have a few questions, and I just want to encourage everyone one more time to enter your questions in the Zoom Q&A or on YouTube if you're there. To start off, there's another question from Bill Phillips. Would random spacing of atoms give n scaling for the output intensity in this last cavity measurement?
Yes.
Okay. Another question is I think this goes back to the first part of the talk, from Chen-Wen Chu, is there some dissipative mechanism in the stabilizer? Wasn't sure exactly when this question was asked.
Okay, this is probably about the autonomous feedback. Is that right?
That could be, yeah.
Interpret this as being about the autonomous feedback section. So let me go back there. Right. So where does the entropy go? So this is an autonomous feedback system that operates essentially as a kind of reservoir engineering. That's the other language that people use to describe it. And it's a driven dissipative system. So In such a system, we imagine that there's like an energy sink, and it works in a way that the initial state of the system, which we regard as some information, is sort of spit out, written down somewhere, but spit out so that the final state of the system, regardless of the initial state, is the same. So that would be, in fact, in our system, I should have drawn a little dashed line off here. This is our controller also has a dissipation channel, and that is the light that comes out of the optical cavity. And as I pointed out, the light that comes out of the optical cavity is recording the history of what the atoms did before they got to the stable point, and is also incidentally a channel through which we can insert measurement-based feedback. I hope that was if that's not the question that was being asked, I can answer a different one.
Very good. Another question from Zoom here from Ata Almasi. And I'm not sure what this acronym stands for, but maybe you do. Can STED, STED type deactivation help reduce the effect of two close atoms in the previous experiment? Right. Okay. So this is about sort of super resolution microscopy methods that come out of biophysics. Okay. And the question is whether if we were to trap atoms, I mean, we're trapping atoms with a lens from up. We have a lens that focuses optical tweezers down. The optical tweezers are distinct from one another. And as such, that means that I have sufficient resolution to send light from above onto each atom individually. So I'm not sure that I need some other sort of optical shelving technique to achieve a super resolution in this particular case. Very good. And related to this as well, Christian asks if stronger tweezer confinement could help minimize the Debye-Waller factor and the related effects. Have you tried to observe that? Yeah, so stronger tweezer confinement plus lower temperature. So if we can apply laser cooling to the system, maybe even sideband cooling to get the atoms down really to the ground state, that would reduce the Debye-Waller factor. And so, yeah, for a lot of the tweezers for cavity QED kind of applications, it would, well, actually for almost everything, it would be nice to position the atoms essentially as delta functions so that we, unless we're interested in their mechanical motion, so that we know exactly what is the coupling to the cavity field rather than there being some uncertainty. So we've been thinking a lot about that. For experiments such as the sort of Dickey phase transition work that I was envisioning, the mechanical degree of freedom is the thing that is undergoing the transition. So I don't think we have the liberty of both cooling it to zero and also asking it to respond. And in fact, I think as we explore it, we'll definitely emphatically be thinking about the Dickey phase transition as being a cavity optomechanics effect, and thinking not just about the phase transition itself, but also what does optomechanics look like in this constructed array of atoms? You know, if you position, I don't know, 4 atoms at particular locations in the cavity, and you wanted to study things like optomechanical cooling of a 5th atom, you know, how does it depend on the positions of the other atoms, the forces that are mediated by the light field, and you know, what is the dissipation like? So that collective optomechanics is definitely going to be something that we are interested in examining. Very good. One more question from Bill Phillips is, are the atoms always spaced far enough that interactions don't mess up the classic Dickey situation? Right. So so in the whatever, you know, there is also the direct sort of dipole interaction between atoms, and in this particular case, we have the liberty of spacing them a fair distance. So you saw that they're already at minimum 4 wavelengths away from each other, and that's simply determined by how close we want to put 2 optical tweezers that are produced by acousto-optical deflectors. We have been thinking about deliberately trying to get the atoms close enough so that there's also direct interactions between them, and then in a very controllable way, seeing both a collective emission into a cavity, but also, you know, other sort of near field superradiant effects happening at once. And yeah, maybe some competition between them, I guess, could be interesting. Follow-up from Bill also was about the back action. Isn't measurement-based feedback dissipating by its nature?
It's yeah, well, it's noisy. Is it dissipative by its nature? Yes, because your quantum system is dissipating information. Yeah, is emitting information. Yes, right.
All right. Well, I think that's actually well, it's been a lot of questions, and I think that's all of them for now. I guess if there's any last questions, we'll hang out here for a minute, but I just want to thank everybody, and Dan especially, for a really lovely talk. Like I said at the beginning, this is our last talk of the season, so stay tuned for announcements in the fall about restarting this series. I think, APS is keen to keep supporting it. It's been really valuable to bring all these talks, I think, really all over the world. We see a lot of viewership everywhere, and really welcome everybody to join these talks. So with that, maybe I'll just say thanks to everybody. Thanks, Dan, once more time. And we'll hope to see you either at conferences this summer or back here in the fall.
Awesome. Thanks.
Right.